Hello everyone, today let's solve the problem number 572, subtree of another tree, right? So what the question states here, we are given two binary trees, nothing but root and subroot. So we are given two binary trees. Let's come to the example part here. Just give me a second here. Yeah, we have been given two binary trees here. One is root and another one is subroot. This is fine. So we have to determine whether subroot is a subtree of root. So subroot, this one is a subtree. Whether this is a subtree of root or not, that we need to determine, right? What is subtree means here? What does subtree mean here? So a subtree means a node in the root. A subtree means a node in the root along with all its descendants should match the subroot in both structures. Again, I'm telling, just keep this in mind. This will be very important. Just listen to this carefully. A subtree means a node in root along with its descendants should match the subroot in both structure and values. So here if we are considering 412, we are having 412. All the descendants are same here. That's what they have marked here on the circle, right? 412. So this doesn't have any subtree here. This doesn't have any children here. So one doesn't have the child node, right? One doesn't have children and two doesn't have the children as well here. So 412 here, this matches. So in this case, we have to return true, right? So we have been given two binary trees, root and subroot. We have to determine whether subroot is a subtree of root. A subtree means a node in root along with all its descendants should match subroot in both structure as well as the values. Both structure as well as the values. All its descendants, they have mentioned root along with all its descendants, right? So root here in this case we will be considering 4, right? 412, right? So 412, this matches completely, right? So this is fine. In this case we will return, we have to return true if it matches, right? So let's come to the second example here. So here we have the subroot 412. So here we have the subroot 412. So this will be considered root here, this one. So this one 412 here does not match because what happens here is 2 is having the child node 0 here. Left subtree we are having for this particular node 2, right? So this one along with its descendant, it has to be the root along with all its descendants should match the subroot they have given. So this doesn't match here in this case, right? So 2 is having the subroot 0, but here in this case we are not, subroot is not having the value 0 or the left subtree or the left child here which contains the value 0. It is not having, right, in this case. So this doesn't match accordingly with the question. So we have to return false in this case, right? So we have to return false in this case. You can clearly see here, right? So this is fine. So let's just give me a second here. Let me clean up this one first. So yeah, first let's discuss the approach, right? I hope the question is completely clear and what we need to do is completely clear as well. They have given wonderful examples just for the sake of understanding, right? So this is fine. So first let's discuss this one approach followed by the edge cases one by one and then finally write the code and discuss the complexities for the code that we have written. So first let's discuss the approach. So first thing that we need to keep in mind here is we will be going with a recursive DFS approach, right? So we'll be going with a recursive DFS approach. So I have considered the first example, the same example that they have given in the question, the first example that they have given in the question, so that it will be easier to understand, right? So here in this case, 3, 4, 5, 1, 2, right? So just give me a second here. So yeah, we have 1 and 2 right here. This is fine. So for this is root, and for the subroot we have here 4, 1 and 2. So this is fine. We have already discussed this one, right? This is structure and values completely different. This one, structure and values both are equal here in this case, right? Also the descendants, right? Also the descendants of 4 here. It starts from 4, 1, 2. We don't have any children for 1 or 2 here, right? So we don't have anything here. So it is completely the structure and values along with its descendants matches here. So in this case we have to return true, right? So output I have not written here. Let me write here output equals true in this case. This is fine, right? So we know this one. Let's discuss the step-by-step execution. First, we will be starting at the 3, node 3, this one, main one. So let me change the color, just give me a second here. This one, from here we will start, right? So start at the node 3 is same tree of 3 comma 4. This one is false, right? Is same of 3 comma 4. This one is false because we don't have the root here. In the subroot we don't have 3 mentioned, right? So here this will be false. We will check the left subtree. Is subtree of 4 comma 4. So this one is subtree of 4 comma 4, this one and this one, right? So this one matches right here, this one matches, so we will return true in this case. This is fine, easy to understand. Let's move on with the second edge case here. At node 4 we will check for the match with subroot, nothing but 4. At node 4 we will check for the match with subroot 4, right? So this is fine, this also matches in this case, right? So this matches in this case. So what we will do, we will 4 comma 4 we will return true. First thing, we will check left is same tree of 1 comma 1 here. In this case, this is also true here. This I'm speaking of 1 comma 1. So this is true, right? So this is true. So just give me a second here. Just give me a second. This is fine. So we will check right is same tree of 2 comma 2, right? So is same tree of 2 comma 2. So this one matches as well. So I forgot to mention this one. So this is not there, right? So this we are not considering. So 2 we will check. Actually this matches as well here in this case. 412, 412, right? So 3, this fails. So this one and this one we are not considering, right? First one was false. We have already discussed this one, right? So we are only considering with the subroot. So here in this case, we will check for the right of is same tree, nothing but the recursive approach we are going with, right? So this is the function name, is same tree of 2 comma 2. This is true here in this case. This is true, this is true. So both matches here, right? Both matches, same tree of 1 comma 1, this one and this one 2 comma 2, this one. This is true, right? So both matches here along with 4 comma 4. 4 comma 4 means here in this case this will be the root when we consider, right? 4 1 2, all the 3 things matches here along with the root. These both matches and this one also matches, right? 4 1 2, root and subroot. So both match here, so we have to return true, or true is returned in this case. Simple to understand, easy to understand, right? So this is the approach that we will be basically going with recursive DFS. You saw this one, right? We saw this one step by step. So this is the approach that we will be basically going with, right? So this is fine. Now we are completely familiar with the approach. So let's discuss the edge cases one by one, right? So let's discuss the edge cases one by one. First thing here is subroot is empty. We have the empty subroot here. In this case, this is true. So just keep this in mind. This is the base case, right? So subroot is empty. When I say base case, an empty tree is always a subtree of any tree. We know this one, right? An empty tree is always a subtree of any tree. Just keep this in mind. This will be the base case basically when subtree is empty. Let's move on with the second edge case here. Root is empty, but the subroot is not. Here the root is empty, but the subroot is not. What, and non-empty tree cannot be a subtree of any empty tree. We know this one as well, right? So in this case we will return false. Simple, right? So let's move on with the third edge case here. Subroot is a leaf node. When I say subroot is a leaf node, I am just going with a root 1 2 3 here. This is fine. This one subroot we have 3. Subroot we have 3. A single node tree can match a leaf node. It can match a leaf node, right? So in this case we will return true, right? In this case we will return a true. So let's move on with the fourth edge case here. Structure matches but the values differ here. You can clearly see 3 4 5 1 2 we have, but we have the subroot we have 4 1 3. Subroot we have 4 1 3. You can just draw the tree and you can just check, right? It will be easier to understand. I'll just leave it for you guys. So this will be false because the structure matches. Quite obviously the structure of the root and subroot matches here, but the subroot has 3 here. Subroot has 3 instead of 2. So this one it should contain here. In this case we should be having 3. Just draw the tree and you will just get to know. Structure matches, but the subroot has 3 instead of 2 here, right? So this is subroot has 3 instead of 2. This one, sorry. So I just got confused here. Right, subroot has 3 instead of 2 here. So this is fine. So let's move on with the edge case. So this we will return false, right? So let's move on with the final edge case here. Tree exists in a different order. You can clearly see here. 3 4 5 1 2 we have, and 4 2 1 we have here in this case, right? So order of the node must match exactly. So order of the node has to match exactly. In this case, it doesn't match, right? So in this case, order of the node doesn't match, so we will return false, right? So in this case, we will return false. We have to return false, right? So these are the 5 edge cases that we need to keep in mind. Subroot, first one is for subroot is empty. The second one is for root is empty but subroot is not. The third one is for subroot is a leaf node. The fourth one is for structure matches but values differ. And the fifth one is for tree exists in a different order. These are the 5 edge cases that we need to keep in mind. Just keep this in mind. This is very important, right? So now we are completely familiar with the approach as well as the edge cases. Now we know, right? So as we are familiar with the approach and edge cases, it will be, we are good to write the code, or it will be easier to write the code. Let's start writing the code. So the first case here is the base case. We know if the main tree is empty, then no subtree is possible at all. So I can just write here, if root equals null, then we have to return false in that case, right? So let me return false here. So we have to check whether the trees are same or not, right? So I'll just be making use of the helper function in this case. Let me quickly write here private boolean. So I'll just make use of the name here, the function name I'll just give here same tree, right? So I'll just give here, we are checking whether the trees are same or not, right? So that is the reason I have considered the name is name this one, function name is same tree. So this will be tree node. Let me consider P and Q. Just go with tree node Q here. This is fine. So here in this case, first what we will check, we have to check whether if both nodes are null. So if both nodes are null, then they are said to be identical. The first edge case that we discussed. So here in this case, if P equals null and if Q equals null, then what we need to return here in this case, we have to return true, right? So this we have already discussed, this one. So the next thing here is if one is null or values doesn't match or values don't match, sorry, then we have to return false in that case. So if P equals null or Q, this one equals null, or value of P not equal to Q dot val here, in this case we have to return false. This is fine. The final step is we have to recursively check left and right subtree. So in this case I'll just return, we are recursively checking, right? I'll just copy the function name here is same tree of P dot left comma Q dot left. Also we have to check for the right subtree as well. So here I'll just go with the same function name, we are recursively checking. So I'll just give the function name here. For the right subtree, I'll just give here P dot right comma Q dot right. This is fine. I hope this is completely clear. Let's move on with the next step here. So just give me a second here. So now we have completely written the helper function, right? So in this case, let's make use of the helper function. Means if both trees are identical, then we have to return true, right? So that's what the question asks. So if both trees are identical, then we have to return true. So I'll just make use of the this one helper function here, function name root and subroot. So they have clearly mentioned in the question root and subroot here. This one I'm going to see here. So just give me a second here. Root and subroot, right? So that's what we are considering here, root and subroot. So if both trees are identical, then we have to return true. If this one root comma subroot, if is same tree is nothing but the helper function name, this one root and subroot, if both are same, then we have to return true in that case. This is fine. So let's move on with the final step here. So we have to recursively check left and right subtrees here as well. So I'll just go with return. So recursively, let me copy this function. Return is subtree. So just give me a second here. Is subtree of root dot left here in this case. This one subroot. This is fine. Or so we have to go with the right subtree as well, right? So I'll just go with is subtree of instead of root dot left, I'll just go with root dot write here, and we have to check for the main root and subroot. So I'll just mention subroot here. This is fine. This is it for the code. Simple to understand, right? Let me format the code once and let me hit the run button. So we have error here. Let's check first thing. So yeah, I have misspelled boolean here. Let me give one more here. So let me run the code again. So I hope this time it has to work. Let's see. So yeah, you can clearly see here the sample test cases are getting passed. Let me hit the submit button. Let's see whether this works for all the test cases or not. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct in this case, right? So let's quickly discuss the complexities for the code that we have written. Right? Let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is recursive DFS or recursive tree matching with DFS. Either way, we can call it, right? So what will be the time complexity here? The overall time complexity would be big O of n into m. Why it is big O of n into m here? N is nothing but here nodes in the root, and m is nothing but nodes in the subroot. We are considering nodes in the root as n, and this one nodes in the subroot we are considering as m here in this case. So in the worst case, for each node in the root, we have to compare all the nodes in the subroot, right? We have to compare all the nodes in the subroot in the worst case, right? So for each node in root, we have to compare all the nodes in subroot in the worst case. So overall time complexity would be quite obviously because of n into m in this case. So what will be the space complexity here? So overall space complexity, we are making use of the recursive stack space here, right? So for the skewed tree, in the worst case for the skewed tree, as we are making use of the recursive stack space, it would be big of n. So for the balanced tree, it would be big of h, right? Big of h for the balanced trees, where h is nothing but the height of the tree, right? So let's consider here big of h. So let's consider here as big of h, right? So the time complexity is big of n into m, and the space complexity is big of h for the code that we have written. I hope the complexities are clear, and I hope whatever the code that we have written is completely clear as well, right? For now, this is it. Thanks for watching, guys.